In this video, we will review the mathematical operator known as divergence and explore its applications in an intuitive way. Before we dive in, I want to take a moment to thank all of you who have shown your trust in me by subscribing to my channel. Your support is incredibly motivating and inspires me to create more content. Thank you so much for being part of this journey. Now let's get started. The divergence is the term used to describe the result of the dot product of the Nabla operator and a vector v. It is a scalar quantity. If the vector is expressed in Cartesian coordinates, the differential operator can be directly applied, resulting in the following formula. It essentially represents the sum of the variations of each component of the field along the direction of that component. The concept of divergence can be understood by analogy with fluids. To better grasp the concept of divergence, let us visualize how the flow of a vector field behaves at different points. Positive divergence, source behavior. Imagine a point in space where vectors radiate outward, similar to water flowing from a spring. This corresponds to positive divergence, indicating that flux is being generated and moves away from the point. Negative divergence, sink behavior. At a point where vectors converge inward, like water being drawn into a drain, the divergence is negative. This represents flux being absorbed at the point. Zero divergence, no net flux. When the inflow and outflow of flux around a point are balanced, the divergence at that point is zero. For instance, this occurs in an incompressible fluid, where no net creation or absorption of material takes place. It is important to note that the presence of partial derivatives is not coincidental. They indicate the tendency of field lines to diverge or move apart from one another. In other words, they measure the deviation from volume conservation. Here are two examples to clarify this concept. Concentric and parallel vector field lines. Imagine a vector field with concentric and parallel field lines. If we place a small gas bubble between these lines and let it move along the field, its volume remains constant without deformation. In this case, the divergence of the field is zero, indicating conservation of volume. Radial field expanding from the origin. Consider a radial field that extends outward from the origin in all directions. If the same gas bubble is placed in this field, it will experience expansion and no longer conserve its volume. In this case, the divergence is non-zero, signifying a lack of volume conservation. Hope this video is helpful. Thank you for your attention. Please subscribe. This motivates me to continue.